Well, the purpose of this video is to review the concepts from Unit 13, which is all about gas properties and the gas laws. We're going to start by noting that there is this information which may be helpful as we are working through some of the mathematical problems. But conceptually, let's talk about the properties of a gas. First, gases have no definite shape or volume. And what this really means is that if you put a gas into a container, it will spread out and fill up that container entirely, which is different from a liquid. If you put a liquid into a container, it will only occupy the space at the bottom of the container. But a gas, because the particles are not attracted to one another, they'll just separate and spread out and fill up the entire volume of any container. Secondly, gases are easily compressible. This is, of course, because the particles in a gas are so far apart from one another that if you put a little pressure on that volume of gas, it will force those particles closer together. And so they're easily compressible because the particles are so far apart to begin with. Third property is that they are easily affected by changes in volume, temperature, or pressure. So they're affected by changes in volume, temperature, or pressure. If you change the pressure, temperature and volume is going to change of that gas. They're all kind of interrelated. All right, so the kinetic theory of gases is meant to sort of explain these properties based on molecularly what is happening inside of a gas. So one of the things that we know is that gas particles move very, very fast. And they move very, very fast. So we say that they have a high kinetic energy. And kinetic energy, which is, of course, the energy of motion. So gas particles move very, very fast. We also know that gas particles... There should be an S up there. Gas particles are very far apart from one another. This is to distinguish them from liquids or solids, where liquids, the particles are close together. Solids, the particles are close together. But in a gas, the particles are very far apart. The distance between particles is huge compared to the actual volume of the particles themselves, which is essentially, so it makes the volume of the actual space that the particles take up is essentially nothing because the distance between the particles is just so great. Third, we say that gas particles move independently from one another. So what this means is that the particles are not attracted to each other. There is zero attractive forces between the particles, which should make sense because if there were strong enough attractive forces between the particles, then the particles would be close together. So we are kind of making those 2 points kind of side by side. Zero attractive forces between particles, and therefore the gas particles don't need to be close together. They'll end up being very far apart, and therefore they can move independently from one another. Fourth, we got to add a fourth one here, is that gas particles have elastic collisions. And so what this means is kind of hard. We don't really know this is not a familiar experience in everyday life. Normally, if you have two things collide with one another, they essentially lose some energy in that process. Energy gets transferred. But in gas particles, when they hit each other and the total kinetic energy is not lost. It might be transferred from one particle to another, but there's a perfect elastic collision when gas particles collide. Moving on to page 2, talking about definitions of temperature, pressure, and volume. So temperature is defined as the average kinetic energy of, abbreviated of course as KE. It's a KE. The average kinetic energy of all the particles in a particular, in a sample of matter. Okay, because individual particles could be moving at different speeds, different kinetic energy, but overall there's an average kinetic energy, and that is what is measured as temperature, but not just any temperature, specifically Kelvin temperature. So we're talking about Kelvin temperature here. Absolute zero is defined as the temperature at which all kinetic energy, which is of course motion, ceases. Okay, when all kinetic energy ceases, I guess I should have the word when there. The temperature when all kinetic energy ceases, that is what is called absolute zero. Absolute zero is equal to 0 degrees Kelvin, which is equal to negative 273 degrees Celsius. So converting between Kelvin and Celsius, Kelvin is equal to the Celsius temperature plus 273. Okay, I think you've worked with that already. So examples, if you convert 234 Kelvin to Celsius, we're going to put the number 234 in for the K. Celsius is, C is going to be our X, plus 273. So solving for C, we have to subtract 273 from both sides. And so Celsius is therefore negative 39 degrees Celsius. Okay. Converting 43.7 degrees C to Kelvin, we have Kelvin equal to Celsius plus 273. So just substituting in the 43.7 in for the Celsius, right? So plus 273. Kelvin temperature here is going to be 316.7 degrees Kelvin. Okay. Pressure. Pressure is defined as the force exerted over an area, and it results from collisions of gas particles. Collisions in the gas particles, the collisions of gas particles on the walls of the containers. Every little particle, when it hits the wall, exerts a force. So collectively, those add up, and that's what we can measure as pressure. So we can measure pressure in a couple different units. We have to know that standard pressure is 760 millimeters of mercury. That is equivalent to 1 atmosphere, which is equivalent to 101.3 kPa. Yeah, I know you wanted to say kDWV. Nope. All right. Converting 5.2 atmospheres. So this is where we need to do a conversion fraction. 1 atmosphere on the bottom, so it'll cancel. 101.3 kPa on top. So you can see atmospheres will cancel. So 5.2 times 101.3 ends up rounded to 530 kilopascals. Converting 5.2 atmospheres to millimeters of mercury. We need 1 atmosphere on the bottom to cancel. 760 millimeters of mercury on the top. Atmospheres will cancel out. The answer here ends up being 3,952, which if we round it to two significant figures, we get 4,000 millimeters of mercury with a bar over the hundreds place. Volume is defined as the measure of the space occupied by a sample of matter. So this is something you're probably very familiar with. Converting between milliliters or liters, you need to know that 1 liter is equal to 1,000 milliliters, and we'll be using that to convert 247 milliliters using a conversion fraction where 1,000 milliliters is on the bottom and 1 liter is up top. So you can see here that this is going to be 0.247 liters is the answer there. And if we have liters trying to get to milliliters, we know that 1 liter is equal to 1,000 milliliters. So in this case, we're multiplying by 1,000 So this ends up being 2,340 milliliters. Okay, so you should be able to convert between the different units of volume. You should know how to convert between the different units of pressure, and you should know how to convert between Kelvin and Celsius for temperature. Okay, in terms of understanding the relationships between these variables, pressure and volume, assuming temperature is constant, has an inverse relationship. Sometimes it's called indirect. Pressure and temperature, as the temperature goes up, pressure goes up because the particles are moving faster and therefore they hit harder. So that is a direct relationship. Volume and temperature, as the temperature increases, particles start moving faster and they start spreading out. So this is a direct relationship. And then the fourth one here is N, which is the symbol for moles. Sometimes you'll see in the Pivnert equation, N is the number of moles. So the more particles you have, the greater the volume will be. So in this case, we have a direct relationship. All right, reviewing the combined gas law, P1V1 over T1 equals P2V2 over T2. This is where you can predict the pressure or the volume or the temperature of a gas if you change the other variables. Okay, so key things to remember: the pressure units have to match. It does not matter if they are both in kilopascals or if they are both in millimeters of mercury. They just need to match. Volume, again, they must match. It does not matter if they are both in milliliters or if they are both in liters, but they must match. Temperature units must match, but they must both be in Kelvin. So you have to make sure that if you're given Celsius temperatures, that you have to convert them to Kelvin. All right, so let's take a look. If you were asked a problem where you had to solve for the second volume, then what you should do is rearrange. So if you keep your eye on V2, that's what we want to solve for. But the first thing you're going to want to do is cross multiply, because that equal sign tells you to cross multiply. So when you do that, you're going to see that the equation's P1 times V1 times T2 is equal to T1 P2 V2. Remember, we're solving for V2, so that means we need to divide both sides by whatever is being multiplied by V2. And what you do to one side of the equation, you got to do to the other. So now we know that this is the equation rearranged for V2. If we wanted to instead rearrange and solve for T2, okay, well now we're looking for that variable. Okay, again, we're going to cross multiply. Right, so we start with that same basic rearrangement. P1, V1, T2 is equal to T1, P2, V2. Remembering what it is you're trying to solve for, which is T2. So you're going to divide both sides by P1 and V1. And so now you can see that T2 is equal to this equation. All right, so Avogadro's law is essentially saying that if you have two gases, right, doesn't matter if they are the same gas or if they are different gases, but if you have two gases and they have equal volumes, meaning they're the same size, and we're going to also assume that pressure is the same between the two particles and temperature is the same between the two samples of particles. Okay, so assuming that you have two volumes of a gas, they have the same volume, they have the same pressure, and they have the same temperature, then what you can then assume is that they both have the same number of moles of particles. Okay. So what that is essentially saying is that with an increase in the number of particles, there is going to be an increase in the volume, right? So essentially that is what is Avogadro's law. It interprets to that relationship. All right, let's take a look. Ideal gases, as a definition, is that it is a gas that obeys the gas laws. All right, and then at all pressure and temperatures. Okay, so any gas is an ideal gas. So all you need to do is to make sure that that gas is behaving as gas-like as possible. And the only way to make a gas behave gas-like is to give the opportunity for the particles to be very far apart from one another. So what that means, do you want high pressure or do you want low pressure to ensure a gas behaves ideally, like the most gas-like? So what we want is, actually we want low pressure, because this allows the gas particles to spread out. And when they are spread out, then the particles don't have any influence on one another, and that is the most gas-like condition. We also want high temperature for gas to behave ideally, because this allows the particles to move very, very fast. And so ideal conditions for a gas would be low pressure and high temperature. If you had a gas at the opposite of those, high pressure and low temperature, so cold and under a lot of pressure, well, that's going to force the particles to slow down and get close to one another. And in that case, you're not going to have a gas, you're going to have a liquid. So you can think about it that way, and maybe it's might make some sense. All right, so talking about the ideal gas law, we've got PV equals nRT, where the pressure, right, so this is pressure, volume, moles, temperature, and then there's something called R, which is the universal gas constant. I don't really care if you know what the name of that is, but it has this value, 0.0821 atmospheres, liters over moles Kelvin. That's always the number that's going to get plugged in for this R right here. The pressure unit, therefore, must be in atmospheres, because it needs to be the same as this pressure unit right here. The volume unit needs to be in liters, because that's liters in that gas law constant. Moles is in moles, and temperature is in Kelvin. So in this case, not the units have to match, yes, but they also have to be very specific units. Okay, we're going to ignore this because we did not do that lab. It's not a great lab, so we are not doing it, especially from distance learning perspective. All right, so these last couple pages are giving you practice with an ideal gas law problem and a combined gas law problem. This is in a free response format, as if you're going to take a free response test. In the year 2020, we are not, in May of 2020, we are not doing a free response test because we are doing this from a distance learning perspective, but we're still going to work through the problem because it's helpful. So here's the question. It wants to know how many moles of a gas are contained in 8.90.0 milliliters at 21.0 degrees C and 750.0 millimeters of mercury. So here I've kind of told you to use the ideal gas law, but how do you do that without being told? Because that's quite likely that you're not going to be told what to use. Well, one of the key things here is moles. The ideal gas law, PV equals nRT, where N is moles. That's a pretty big tip that you're going to be using that particular equation. Okay, so a couple of things. The pressure was given to us at 750, so that's our pressure right there. But the problem is, for the ideal gas law, remember the universal gas constant is this number, 0.0821 atmospheres, liters over moles Kelvin. So we have to have a pressure unit that's in atmospheres. They gave it to us in millimeters of mercury, so we need to do a quick side conversion. Right, so 750 millimeters of mercury. We're going to put 760 millimeters of mercury down here, so the millimeter mercuries will cancel. 1 atmosphere is up here. So millimeters of mercury cancel, and the 750 divided by 760 ends up being 0.9868 atmospheres. So that's the converted answer. The temperature in this case is 21 degrees Celsius, but we need to convert that to Kelvin. So Kelvin is Celsius plus 273. Celsius temperature 21.0 plus 273. And so our temperature here is 294 Kelvin. Okay. The volume is being given to us at 890.0 milliliters, but we need a unit in liters, so we have to divide by 1,000 milliliters. So this is going to end up being 0.8900 liters. So now we know our pressure in the right unit, we know our temperature in the correct unit, and we know the volume in our correct unit. So what we now need to do is set up the equation. We are being asked to find how many moles, that's N. When we rearrange this, we're going to have N is equal to PV over RT. So now this is a matter of substituting our numbers in. N is equal to 0.9868 atmospheres. Plugging in our volume, 0.8900 liters, divided by our gas constant. Make sure you have all 4 of those units in there. And then the temperature is 294 Kelvin. So we can see here that the units of atmospheres are canceling. We can see that kelvins are canceling. We can see that liters are canceling, and the only unit left there is moles. So we're going to see that our answer here is 0.0364 moles. All right, if we look at the last page, we see that we have a problem right here. A gas has a volume of 800 milliliters. It's at a temperature of negative 23 degrees Celsius, and it's got a pressure of 300 millimeters of mercury. They want to know what would the volume of the gas be, so our V2 is going to be what we're looking for. They gave us a new temperature, so that's our T2, and they gave us a new pressure of 600 millimeters of mercury. So the 800 was our initial volume, the negative 23 was our initial temperature, and the 300 millimeters of mercury was our initial pressure. You might recognize that our temperatures are going to have to be converted into Kelvin first before we do anything else, so let's take a look at that. For T1, we have to take Kelvin and take our Celsius temperature of negative 23.00 degrees Celsius and add 273. So the Kelvin here for this is 250 Kelvin, so that's our T1. And then our T2, Kelvin is equal to 227.0 plus 273. So in this case, our Kelvin is 500 Kelvin. So we've got our T1s and T2s in Kelvin. We know our initial pressure is 300.0 millimeters of mercury. And our new pressure is 600.0 millimeters of mercury. And our V1 is 800.0 milliliters. It's just kind of helpful to kind of sort them out so that you don't have to keep going back to the problem and reinterpreting it. Okay, so now that we have all of our numbers in our data table, let's talk about the how we're going to plug them into the equation. You might recognize that this is a combined gas law problem because you have changing conditions. We know we're trying to solve for V2, so I'm going to circle that. And to rearrange this equation, we're going to cross multiply. So we have P1 V1 T2 equal to T1 P2 V2. Knowing that we're trying to solve for V2, we're going to divide both sides and get this cleaned up. So here's what we have to do to use as our equation to solve for V2. So subbing those numbers in, P1 is 300. P1 is 300.0 millimeters of mercury. V1, 800. T2, 500 Kelvin. All divided by a T1 of 250 Kelvin and a P2 of 600.0 millimeters of mercury. So the units that cancel, millimeters of mercury, Kelvin and Kelvin, leaving us with a unit of milliliters. So when we do this math and simplify it down, we see that we're going to get a volume of 800 milliliters. So it turns out that the volume did not actually change, and that is because the pressure increased by 2, so that would make the volume cut in half, but because the temperature doubles, that's going to bring the volume back up to the original volume. So it's a lot of work just to figure out that the volume doesn't change. But there you go. There's a comprehensive review of the Unit 13 on gases and gas laws. All right, you guys, thanks. See you back in the classroom.